In this video I'm going to demonstrate a simple Mandelbrot shader which I implemented using DirectX and HLSL. First I'll quickly go over the code to show you how it's set up. I first created a simple framework for DirectX to abstract away some of the more complex DirectX stuff so I could just focus on creating the demo. But I'm not going to show you the DirectX stuff too much. I'm just going to show you the implementation. So at the lowest level, we have a application class, and the application class is responsible for doing things like creating a render window. So in the main function, we first create a render window, a DirectX render window, and then we set up a few parameters. We don't really use a world or matrix or view matrix. We simply use an orthographic projection matrix to render a full screen quad onto the render window. We first have to set up our vertex buffers, texture coordinate buffers, and an index buffer to render a simple quad. This is necessary in DirectX as immediate mode rendering is not available, so we always have to use buffers even if we're only supplying 4 vertices. So to create the buffers, we first ask the window to create some buffers. The window is the owner of the DirectX context, so that's why we're always using the window to create the buffers and the shaders. We also have to create a vertex shader. This is just a simple vertex shader, which is basically a pass-through, but it actually multiplies by the world view and projection matrices. But the result is basically a full screen quad from these vertices, where this is the top left, 0, 0, 1, 0, 1, 1, and 0, 1 is the bottom left corner of the screen. And then we load 3 different shaders. The first shader is basically, well, the default one is the Mandelbrot fractal shader, which we load second here. We also load a Julia fragment shader and an embossed fragment shader for the Mandelbrot set. And I'll demonstrate all 3 of those shaders here. Then in order to use those shaders, we set up materials, and materials are combinations of vertex shader or Mandelbrot and the pixel shaders. Potentially we could have additional shaders here, but at this moment I only needed the pixel and the vertex shaders, so I didn't implement geometry and tessellation shaders. And then we need a mesh. Even though this is simple mesh, we still need to create a mesh class, and we add the buffers to the mesh class with the correct semantics defined in the shader. For tweaking parameters, I'm using ant tweakbar. This function just sets up the tweakbar parameters for the ant tweakbar. The ant tweakbar is available online if you just do a Google search for ant tweakbar. The window has several events which you can receive and handle. So whenever the window needs to re-render, it'll fire these events in this sequence: pre-render, render, and post-render. As we'll see later, pre-render is basically setting up shader parameters and clearing the depth buffer. And then the render is the main render function, and then we'll execute our shader depending on what shader we have currently selected. And post-render will basically just present the screen, but it could be used for other things. Oh, and rendering the tweak GUI, the tweak bar. We also need to handle some key press and key release events, so we'll register for those there using this semantics, using this syntax. And we also have a high resolution timer, which I'll use to calculate the delta frame every frame. We need to tick it once. This will initialize the elapsed timer, so that after the next time we get to render, we actually have something greater than 0. And kick off the application with the app.run function. Okay, so every time the screen needs to be presented, the onPreRender function will be called. And for that, we first need to cast the caller into a render window. Well, we know that the caller is a render window, but the class is always specifying it's an object, so we'll just cast that anyways. Then we'll first clear the depth buffer. We don't need to clear the color buffer because the shader will replace all the pixels in this on the screen. There's no optimizations in this shader for doing only the pixels that change, for example, which is a possible optimization for the Mandelbrot shader. Then to get the elapsed time in seconds from the high resolution timer, we use get elapsed seconds. And then we can compute the frame rate based on the delta time, and we're going to do an interpolation between the previous frame rate and the current frame rate. This gives us a little bit of a smoother frame rate. Instead of fluctuating so rapidly, it'll kind of smooth it, but even at really high frame rates, 90% smoothing will not really be noticeable. It'll still look wild and fluctuating, so we could set this to 50% at the risk of getting slower and less accurate frame rate counters. Okay, so the shader variables is a structure which is basically just storing all the different parameters that I can possibly pass to the fragment shader to render the Mandelbrot and the Julia set. I can also use this as a token, so the default parameters will I can use it to specify without doing anything else the default parameters, and then when I hit the reset button I can use them as basically as a token to restore any modified variables back to the default values. So I'm not sure you're familiar with the memento design pattern, but yeah. It has a simple update function which will animate the Julia seed based on the animation direction of the Julia seed and the delta time that is passed. And I also have this feature that you can turn on the optimized frame rate, and what this does is basically it will choose the iterations based on the current frame rate and a target frame rate. So for example, if you wanted to achieve 60 frames per second, which is the default, but you're only getting a current frame rate of 30 frames per second, then it will reduce the iterations from whatever the current is down to, well, 30 less iterations than this. And this will allow the iteration count to rapidly approach the desirable iteration count for the current target frame rate. If we just increase the iteration count by 1 every frame, if it was too slow or too fast, then you'd notice that it takes a long time to actually get to the ideal iteration count, but it probably will result in less fluctuation when increasing the iteration count actually caused the frames per second to drop drastically, and on slower GPUs this can cause a rapid fluctuation in the iteration count. Maybe I will demonstrate that in this video if it happens. So anyways, then we also, because I noticed this fluctuation occurring on some GPUs, I'm just going to average the previous iteration count in this one. This will slowly allow it to converge slightly slower and hopefully reduce the fluctuations. And we also want to clamp the maximum iterations. In some cases, the iteration count can skyrocket. For example, when viewing the Julia set, for some reason, the iteration count skyrockets and it goes well beyond 2,000 iterations, which is still doable at some desirable frame rates on my GPU, but when it starts getting into the higher thousands, then it becomes a little bit unwieldy. And in fact, I even had a GPU crash once. Okay, so back to the pre-process stage. So that was the pre-render. So it's the shader variables update function, explaining that. So depending on the fractal type we're actually viewing right now, we want to we'll first make some variables hidden from the tweak bar, which I'll show later, and we want to make sure that our mesh is using the correct material to render. That's the correct combination of the vertex shader and the pixel shaders. And obviously for the Julia set, we set the Julia material, and we say that we want to use the Julia pixel shader. And for the embossed Mandelbrot set, we'll hide the Julia set parameters, and we add a light direction variable, which we can use to determine the shading on the embossed Mandelbrot set. So depending on the pixel shader we set, we want to set some of the variables, and these are basically all the variables from the shader variable structures I just showed you earlier. And these are all the properties described or defined in the pixel shader, and this will cause those shader variables to become updated. All right, so when we render, we only have a single mesh, so we just want to render that, and we don't need to do anything else. That will kick off the index buffers. Yeah, we'll bind all the constant buffers, bind the shaders that are associated to the current material for that mesh, and update the variables for the particular shader. And when we're done rendering, all we want to do is present. And that will do it for rendering the Mandelbrot set and the Julia set, but we also want to be able to handle certain key codes, so we have to respond to the key pressed events, and if somebody presses escape, we stop. If you press R, we reset the data. Pressing O will toggle the optimization frame rate setting on the that I described earlier, which adaptively adjusts the iteration count. Pressing the left key while viewing the Julia set will move the Julia set in the direction left, or basically reverse in time of the animation direction. And pressing right on the keyboard will cause the Julia seed to move forward depending on the animation direction. So Q, we use Q on the keyboard to zoom in at the origin of the screen, and E to zoom out. I've also implemented mouse scroll wheels for zooming, but if you don't have a scroll wheel, you can use Q and E on the keyboard to zoom in and zoom out. So you can also pan the current origin of the complex plane using WASD keys, and that'll move the view around. So if we on the mouse moved events, I want to handle the left mouse button because I also want to use the left mouse button to pan the Mandelbrot set. And I'm using the mouse wheel event to zoom in or zoom out on the current cursor position. And a brief description of how this works is that we first compute the screen position of the mouse at the current zoom, so the current zoom level before we adjust the zoom, and we call that the fractal position because that's the position on the complex plane. Then we apply the zoom based on the wheel delta, and then we compute the new position after zooming, and then we pan the view by the difference of those two positions. And what that will do is allow us to pan in directly on, or sorry, zoom in directly onto the mouse point, as I'll show you. And the tweak bar, these are all the tweak parameters that are available. Not all of them are viewable at a time. For example, the Julia seed parameters are only visible during when you view the Julia set, and the light direction is only visible when you view the embossed Mandelbrot fractal. All right, let's see how it runs. So let's execute this. We're running in release, and I hope that I get a reasonable capture here. Okay, so it's pretty good. It seems like Camtasia Studio is not affecting my frame rate at all. I'm still getting upwards of 2,000 frames per second. This is pretty normal on this GPU at even 128 iterations. So using the mouse wheel, I can zoom in to one of the points here between the main body of the Mandelbrot set and the head. And we can zoom in further and further and further until we get to one of these points here. And you can see we start losing resolution when we zoom in at a certain point. So using the tweak bar here, I can increase the iteration count. As you can see, that affects my frame rate. It's now down to 600 or 700 frames per second. And zooming in more doesn't give us any more detail at a certain point. As you can see, it becomes pretty pixelated. And the reason for this is simply floating point error. There's just not enough floating point precision to zoom in any further. If we could use doubles for the shader, I'd be able to zoom in a lot more, and we could zoom into one of these curls over here. Okay, so that's the Mandelbrot set, and let's hit reset here. And hitting 1, I can switch to the Julia set. So here's the Julia set at the current seed of 0.93 in the real axis and negative 0.2 in the imaginary axis. And hitting spacebar, we can toggle the animation of the Julia set, which is kind of pretty. And there's also a direction parameter here, which we can adjust the direction of the animation of the seed parameter through the complex plane. So if we go out here a bit, you can see that the Julia set will become this huge black hole in a second here. So it gets larger and larger, and this is how, when it approaches this point here, we get this black plane, and then we can go back and watch it converge again. It's kind of pretty, bit of a gimmick. Makes it hard to zoom in on at any point. We can also increase the iteration count while we're watching it, or turn on adaptive iterations, and you see, using adaptive iterations, the frame rate, even at 120 frames per second, the iteration count stays way above 2000. So and our frame rate is hardly affected. I mean, it's in the thousands of frames per second. So okay, and the last implementation, let's turn down this so we don't get so, whoops, like this 512. And the last one I wanted to demonstrate is the embossed fractal. And basically this is kind of, I don't know, I didn't really see, you can see the frame rate drops significantly here, and it becomes a little bit more difficult to pan in real time. But let's turn this down to 128. Let me get back to 100. But basically what I tried to do here was, instead of computing just one position or one value at each pixel in the complex plane, I actually calculate 5 points. One for the center to determine the color, and then the corner points around that pixel at no more than 1 pixel distance to compute a height value of the Mandelbrot set at those points. Then from those height values I can compute the normal vector on the 2 triangles formed by the quad at those 4 positions, and then I average the 2 normals of those 2 triangles to compute an average face normal for the center pixel. And what we get is a bit of a nicely shaded fractal, basically. And I've implemented both specular highlights here on the edges of the curls here. You see that more apparently, as well as diffuse lighting on the embossed fractal. Okay, that's actually about it, I think. It's pretty fun working on this assignment. I learned quite a bit about fractals I never knew before, and I'm more interested in them now. So yeah, unfortunately I don't have more time to investigate further. I would have liked to implement a proper double precision floating point implementation in the fragment shader for the fractal, so I could get better resolution as I drill down, but unfortunately I don't have time for that, and one of the assignment restrictions was that I couldn't implement double precision in the shader because the GPU that it needs to run on doesn't support doubles in the shader. But the GTX 680 I'm working on now, it supports double precision, so that's not a problem. Okay, thank you for watching.